Good morning, everyone. I want to remind that we are talking about duality, and I want to remind what is duality and what we already know about dual problems. And first reminder, because actually we do know quite a bit about duality, and we talked about it last lecture and one before this. And well, somehow it is important to know all of this to understand what's coming today. So just remind you. We have two problems, the primal and the dual problem. The primal problem is about maximizing the quantity z, which is the sum of some numbers times the variables. And let's say there are n variables. So, as an introduction to what we are going to do next week, talking about matrices and such things, we'll start writing the sums with this short notation. It's sigma, standing for sum, for the variable from 1 to n, of the following expression: c with index I times s with index I. So it's the same as c1 s1 plus c2 s2 plus and so on up to cn s1. And the constraints are subject to the following constraints. Sorry, I wanted this index to be j. Oh, with the compatibility with what I'm going to write next. So here it will be sum for j from 1 to n of aij j smaller or equal than bi. So let's say here we have m constraints, so I for any number from 1 to m, and of course all xj's will be positive. So that's just, well, another way to write a linear programming problem in standard form. You want to maximize a linear function subject to some linear constraints. Some linear functions more equal than some number, and they just wrote it down in this way. The dual problem is about trying to multiply these constraints by some constants, by I, taking the sum, so take the linear combination of constraints, and try to come up with a linear combination which is always larger than this value of z. And then try to find the smallest linear combination in the sense that the linear combination of the right-hand sides is the smallest. So the dual problem is about minimizing this linear combination of right-hand sides, bi or yi. Now the index goes from 1 to what? How many terms do we have here? Same as the number of constraints here, which is m. So from 1 to m. And subject to the following conditions, you want, well, as you sum all these constraints with coefficients yi, you want the sum of coefficients at each xj to be bigger than this cj, the coefficient of z. So you want sum of aij yi to be greater or equal than the corresponding cj. The sum is over all possible constraints, so for I from 1 to m once again. And here we have constraints for each j from 1 to m. And you only want the positive linear combination because multiplying a constraint by a negative number reverses the sign. So you don't want to multiply by a negative number. So you pose the condition that all i's are greater or equal than 0 for I from 1 to m. let's call this function double. So here I did nothing new, hopefully, I mean, except maybe using this notation for sum, but otherwise it is the same pair of problems, general linear programming problem in standard form, and, well, it's dual. So notice that here the summation is kind of, if you put these numbers in a matrix, in a table, here the summation is over the rows, here it is over the columns, as you would expect. And we have proved some very nice theories about this. We have proved some facts. One fact, almost obvious, Z is always smaller or equal than W. We basically constructed the dual problem in such a way that it will satisfy this inequality. The objective function here is bigger, is an upper bound on all feasible solutions here. So for any feasible solution Z and W, we have this inequality. Last time, we also have showed the following fact. If the original problem has an optimal solution, the dual also has an optimal solution, and they equal. So the optimal Z is actually equal to the optimal W. So this is optimal large Z. It exists. And this is the smallest W. So let me remind you some names. The first statement, the inequality, is called the weak duality theorem. It's weak because it doesn't tell you much. It's basically false from the definition of the dual problem. The second one is called the strong duality theorem. If there is an optimal solution to the original problem, the dual also has an optimal solution, and they. And that's not obvious. And let me remind you also what important fact we use to show this equality. We use the fact that you can actually read the solution of the dual problem if you know the last line and the last dictionary in the primal problem. So if the last line in the last for this I wanted to introduce the step variables first. So let's do this. So continue with step variables, all problems. So I will introduce names for the variables which measure to what extent the inequality is far from actual equality. So here it will be S slack variable corresponding to constraint number I is sum of aij xj minus bi. Oh my god. I want it to be positive, of course. It's bi minus the sum. aij xj. But in the dual problem, it is because here I have the reverse inequality. I'll have to first multiply it by -1 and then do this procedure, and the answer becomes sum of aij yi minus cj. So these are just the names of the step variables. Here you have m step variables, same as number of inequalities, as number of constraints. Here you have n. Once again, same as number of constraints, but in the dual problem. Okay, and now I can say what I wanted to say. If the last line of of the last dictionary of the primal is Z is the optimal solution minus sum of x j's with some coefficients which we'll call Cj bar, and minus sum of the slack variables Si with some coefficients which we'll call Yi. So if the last line reads as follows: Z is some number which we know is the optimal value of Z, minus a sum of variables and sum of slack variables with some coefficients, which I call Tj bar and Yi bar. Then I can read the optimal solution to the dual problem from this line. Then Yi just take it to be these coefficients, and Tj take it to be these coefficients, is a solution, is the n optimal solution. I'm going to say n optimal to the dual. So I'm saying here n optimal solution because even if the original problem has only one optimal solution, the dual problem might have infinitely many. It can happen, especially if they kind of, sometimes it happens that you may make another degenerate iteration even after the last one of the simplex algorithm, and this will lead to a different dual optimal solution. But, well, it's kind of degenerate iteration, we won't emphasize it too much. But anyway, the important thing is the coefficients and the variables in the last dictionary of the primal are exactly the values of the slack variables in the dual. And vice versa, the coefficients and the slack variables in the primal are exactly the decision variables in the optimal solution of the dual. Okay, and finally we last time talked about the following fact called complementary slackness. And that's, well, basically a very simple observation about the follows from this line. If one of, well, basically in each pair xj, tj, and xi, yi, at least one of the numbers is 0. So if you know, for example, that xj happens not to be 0 in the optimal solution here, it means that it was a basic variable here. It means that it comes with coefficient 0 in this line. And that's how this thread follows, similarly for this pair. And so from the complementary slackness, we derive a very nice criterion for how to check whether a suggested solution to the primal problem is actually the optimal solution without solving the problem. So to check whether xi is the optimal solution to the primal, check the following things. Xi is feasible for the primal. Compute sorry, I usually write xj, so let me continue writing xj. Compute si, which is di minus sum aij xj. Find all by I satisfying complementary sadness. So write down all the linear equations which follow about the dual solution from the complementary sadness. Typically, you'll find just one possible solution, and fourth step, verify whether at least one of those is feasible for the dual. So if you manage to find a pair of solutions for the primal, one solution for the primal, one for the dual, both are feasible and they satisfy complementary sadness, then for sure you know that you found the optimal solutions for both. So basically the algorithm is like this. Once again, you check that the suggested solution is feasible for the primal problem, you find out what are the slack variables. Using these, we can write down the conditions about complementary slackness. You find all possible solutions to the complementary slackness conditions. They are, for now, they are just solutions which satisfy complementary slackness. They have nothing to do with the dual problem. Almost nothing. But now you take these numbers and you try to check whether they do satisfy the conditions of the dual problem. If they do satisfy, well, you are done. You found the optimal solutions to both the primal and the dual. So all this is a reminder from the last two lectures. So maybe if somebody is confused about one of these points, it's a good idea to ask any questions right now. Because now we'll start talking about a material that builds on these facts.
Just wondering, what is a midterm cover on top?
The midterm will cover variety, I think, together with today's lectures.
So today's lecture will be the last lecture.
I don't know. I have to talk with the other instructor first. Okay. Other questions? Okay, so now we'll start talking about economic significance of the dual variables. So up to now, the dual problem was a kind of funny, interesting tool for us. Its solution was a certificate, a feasible solution of the dual problem was a certificate that our original problem was bounded. Okay, it's very nice. Say this algorithm tells you if you have a suggested optimal solution for the primal problem, you can use the dual to verify that it is actually optimal without solving the original problem. Once again, very nice tool. But what is the meaning of these dual variables, yj? Kind of, what do they mean in practice? Suppose you have a problem, it comes from a factory that manufactures some products. Is it important to tell them both the solution, kind of the schedule, you should produce so many products of type A, so many products of type B, and so on? Is it important for them to know what are the dual variables? well, for now it seems like no. I mean, they're just an artificial tool for us to verify the correctness of our own solution. But it turns out that if you think about what is the actual meaning of these variables, you'll find out that yes, they are very meaningful, very interesting, well, for this factory. So let me try to explain this. And for this I'll start with yes, so I'll start with once again a little bit of mathematics, and then we'll start talking about kind of economics. So the mathematics here is as follows. Suppose we change the constraints the bi in the constraints a little bit. How will the optimal value of z change? So the question is, suppose now instead of, well, you had a constraint, say you had 50 workers, and it was a constraint about, well, your production line, you could only use 50 workers. You found the optimal solution for a problem, you found out that, well, with these 50 workers, you can now get a profit of $1,000. What's going to happen if you change the number of workers by a little? Instead of 50, you'll have now 51, or say 49. How much will the profit change? So it looks like a very reasonable question. And let's try to understand what happens. So we'll use the following fact. The optimal solution of the primal problem is in fact the same as the optimal solution of the dual problem. That's first observation. Instead of computing my optimal value of z, I'll compute the optimal solution of the dual problem. Okay, sounds like a strange first step. I mean, now I complicated my life. Instead of talking about the original problem, I will talk about the dual. But look at the dual. Look at the constraints for the dual. Have they changed when I changed to coefficients bi? No, not at all. So constraints for the dual don't change, don't depend on bi. So for the dual problem, the fact that I changed the coefficients bi, well, it does feel it a little bit in the fact that the objective function has changed. But if I had a feasible solution, it's still a feasible solution. If I had a basic dictionary, it's still a basic dictionary. So if I had kind of two constraints which got pushed to their limits, and I got a point at the intersection of the two constraints, well, I still have it. So I haven't changed the region of feasibility. The all possible numbers yi for which the solution of the dual is feasible did not change. And also I changed my objective function by just a little bit. So I have only, well, that many feasible dictionaries for the dual problem. And at each dictionary means, well, I set some of the variables to 0, and the other variables adjust according to these constraints. So basically, all these dictionaries did not change. The only thing is, for these values of the numbers yi, I now compute not the previous linear combination of yi, not some bi times yi, but slightly different. The thing is that this value is among the all possible kind of candidates for the optimal one. Well, they changed only slightly. If the change is small enough, the one that was largest is still the largest. So if the change in the objective function sum of vi yi is small enough, the same values of yi will give the optimal solution. So maybe let me illustrate this. I'm not going to explain this too rigorously, but I want you to understand what happens. I mean, we will not require you to formulate rigorous mathematical proofs of these facts, but I do want you to understand why it's true. So think about kind of two-dimensional problem, like the one you have on the homework with some two-dimensional constraints, some region, something like this. You want to look only at the solutions which are inside of this, in this case, pentagon. Well, so these are the constraints. Your numbers should be above this line, to the right of this line, and so on and so on. So basically the feasible region is something like this. Now the optimal solution, well, it used to be, let's say, here. And the reason it was used to be here is because now you have over this region a linear function. So if you imagine a graph of this function, it might look somewhat like this. It's a plane. Maybe let me use an actual plane. Something like this. The thing is, over this vertex, I have the point which is farthest away. Now I change this plane a little bit. I change these coefficients bi, it means I change the linear function by just a little. Well, this point which used to be the largest is still the largest. The only way I can actually go from the largest value being here to say being here is by quite a big transformation. I have to actually invert the plane. If I change it only slightly, still this vertex will remain optimal. So basically, if there is an actual difference between the value here and here, if this is 5 and this is 4, before this one becomes larger than this, well, it should be kind of 5, 4. You change it slightly, it becomes 4.9, 4.1, and so on and so on. So in some region, well, for some small perturbation of the coefficients, this will still be the largest. But then, my optimal solution, which is also optimal for the dual, is in fact sum of bi yi. So how much did it change? Well, it's written right here. So if one increases, say, bi by delta, let's say delta bi, or let's say by delta, by some small number, and keeps the other is constant, the value of optimal solution, which is also the optimal solution for the dual, which is also sum of the I by I. Well, in this sum you change only one of the terms, the ith one, and it got increased by bi got increased by delta, and yi is still the same number by I. Like by I times delta. So that it won't be just delta by I. So if you say increase bi by some small unit, delta, the optimal solution will increase proportionately, and the coefficient of proportionality is exactly by I. So, well, at least in mathematical terms, and if you are familiar with, say, calculus, you would say that by I is in fact how much the optimal solution depends on change in vi, and it's called the partial derivative if you wish, or well, it's how fast the optimal solution grows if you change the vi but keep all other ones constant. So if it clarifies something for you, it's good. If it doesn't, it also doesn't matter that much. This is also a good explanation. So let me once again try to parse this conclusion. The mathematical significance of the dual variable using this interpretation is as follows. It's how sensitive the optimal solution of the original problem is to a change in the number on the right side in the ith constraint. So let's suppose that we have a constraint which was about using 50 workers for your production. You solved the original problem and you said that, well, my profit is 1,000. Suppose you now increase the number of workers by just 1. And let's suppose that 1 is small enough compared to 50. And it does sound reasonable. So you increase the number of workers by 1. Now you can use a little bit more capacity. Not just 50 workers, but 51 workers. How much can you increase your profit? The answer is, you should compute the dual variable which corresponds to the constraint about the workers. If it is, say, 20, then one additional worker will bring you a new profit of 1 times 20. 2 additional workers will give you additional profit of 40. Delta additional workers will give you 20 times delta additional profit.
So I'm still not sure about the part where it says small enough. Like, how do we know if it's small enough? Like, when the objective function changes, how do we know that the optimal solution would not change?
Okay, so we'll talk about the kind of quantitative answer to this question much later, towards the end of the course. I mean, exactly how much can you increase the BI so the optimal solution will still be optimal. The qualitative part for us, the answer is that, I mean, for us now it doesn't matter. We just want to understand what is the significance. And I mean, if say 10 workers is too much of an increase, we'll just try to increase by just 2 workers. If 2 workers is too much, we'll try to increase by 1. And if even 1 is too much and you cannot split workers, cannot buy kind of part-time worker, so that maybe didn't make too much sense for you right now, but I mean, but then it also means that the problem is kind of very, very sensitive and very, very degenerate.
So for, say, the matrix that would be generated by any given problem, in terms of the sensitivity, is the condition number defined for a matrix here, or does that tell us anything about the sensitivity of changes?
Don't think that the condition number is, I mean, no, I don't think that this is sensitivity in this sense. I mean, the condition number is more about kind of how the solution to the linear system with the qualities depends on the change in the right-hand side. Here it's quite different. I mean, you have constraints, and you might have a matrix which is kind of quite degenerate in one part of the feasible region, but near the optimal solution behaves very nicely. So I don't think that the condition number captures this.
Is this idea up here with the partials related to like the Lagrangian constant at all?
Yes.
Okay.
Yes. So if you were to talk about nonlinear optimization, these i's will be exactly the Lagrange multipliers. Once again, I don't want to bring this right now because it's not formally part of prerequisites of this. Other questions? Okay, so let me give a kind of, let me first check whether I skipped over something. Okay, so let me try to give a kind of down-to-earth example with numbers and with well, something very concrete, so that we'll have a concrete understanding what is the meaning of these low variables in economic terms. So suppose we have the following example. You have a production and you produce two products, chairs and tables. And the resources for producing the chairs and tables are as follows. So for a chair, one chair, you should use 3 units of wood, 2 units of metal, and 2 units of labor. I don't know what kind of units there are, maybe hours of work, and here it may be some bolts, and here it might be kilograms of wood. And for tables, the corresponding figures are 4, 1, and 2. You also know how much of the resources you own. So total amount of resources that you can use is 50 units of wood, 50 units of metal, and 30 units of labor. That's what you have, your capacity. And the profit that you're going to derive from producing, say, one chair, will be $20, and the profit from producing one table will be $10. And the question is, of course, try to find the optimal production strategy, try to maximize the profit. Well, for this we know what we have to solve. So our problem is about maximizing the profit. Let's say that we produce X1 chairs and X2 tables. So we want to maximize 20 X1. From each chair we derive $20 of profit plus 10 X2. Subject to the constraints that we don't use too many resources. That we don't use too much wood, too much metal, and too much labor. So subject to the constraint about the wood. By producing X1 chairs and X2 tables, we'll use 3X1 plus 4X2 units of wood, and we don't want to use more than 50. For metal, will use 2x1 plus x2 units of metal, and we don't want it to be larger than 50. And for labor, we'll use 2x1 plus 2x2. And we don't want this to be larger than 30. And of course, we want to produce positive amounts of tables and chairs. So that's the linear programming problem which corresponds to this kind of factor. Very simple. In fact, the way I've written it, it's kind of almost the linear programming problem in the table form. Almost. Okay. Now suppose we will not solve this problem right now. Instead, we'll start talking about, we got bored with this business, we want to sell it. And the thing is, we don't want to sell it too cheap. We still want to get the same amount of, at least the same amount of money that we will get from actually producing the chairs and the tables according to our optimal solution. Well, the problem is, I don't really know what is my optimal schedule. Somehow, I lost the papers, I don't know, I don't want to solve this. So I'll come up with the following strategy. I'll only sell the wood, the metal, and labor. I will actually sell all the 50 units of wood that I have, all the 50 units of metal, and also the 30 units of labor. And I'll set the prices for the wood, metal, and labor in such a way that by selling 3 units of wood, 2 units of metal, and 2 units of labor, I'll get at least $20 for such a transaction. And also, if I sell 4 units of wood, 1 unit of metal, and 2 units of labor, I'll get at least $10 from such a transaction. This will ensure that whatever my schedule is, I will still get more money from actually selling this wood, metal, and labor than if I would convert it to actual production of chairs and tables and derive the profit from actual sale of chair and the table. So I'll set the prices of wood to be Y1, of metal I'll set it to be Y2, and for labor I'll set it to be Y3. So my fairness conditions are as follows. I want to sell, once again, if I sell 3 units of wood, I'll get 3 times Y1 dollars. If I sell 2 units of metal, I'll get 2 times Y2 dollars. And if I sell 2 units of labor, I'll get 2 times Y3 dollars. I want this amount to be at least as large as my alternative plan. Actually using the same units of wood, metal, and labor to produce a chair, sell it, and get $20 of profit. So here I want to get at least $20.
Where do you get the constraints for the primal from?
The primal,
Yeah.
so this constraint is about not using more wood than I have.
Oh,
So the amount of wood that I use if I produce x1 chairs, x2 tables is 3 times x1 plus 4 times x2. And I don't want this to be larger than 50. Okay, so back to here. This tells me I want to set my prices so that it will be more profitable to me to sell the units of wood, metal, labor like this than actually converting them to a chair and selling the chair. If this condition is satisfied, I know that I'm better off selling the resources than actually converting them to chairs, actually producing. Well, I also don't want to sell the wood, metal, and labor in such a way that I would be better off making the table. So I want to impose a condition that 4 times y1 plus 1 times y2 plus 2 times y3. So the amount of dollars that I will get by selling 4 units of wood, 1 unit of metal, 2 units of labor, well, I know that using my production, I can convert them to actual $10 of profit. I want, by selling these resources, to get at least as much. So these conditions are my fairness conditions. Well, of course, I don't, well, I want all the prices to be positive. I don't want to pay anyone. I want to get the money from somebody. And, okay, so any kind of offer which will satisfy these conditions will give me, well, profit which is guaranteed to be better, or at least as good as the profit that I'll get from the optimal production here. Because once again, by selling the, I mean, if I can really convert between resources and the chairs, or resources and the tables, well, I'm kind of indifferent whether to sell this amount of resources or selling one chair, for which I get 20. And if I can get more than 20 for these resources, well, I'll be happy. So this is about this, and the second line is about that. But now let's say I actually come to the market and I tell them, you know what, I'll accept any offer which satisfies these constraints. And the market tells you, well, you know what, I am willing to buy those, but I don't want to overpay. I want to find the smallest possible prices, the prices that satisfy these constraints which you gave me, but I want to pay the smallest possible price for a business. Well, but what is the price that I will pay for a business? It is, I'll buy from you 50 units of wood, plus 50 units of metal, plus 30 units of labor. So that's the price that I will pay. I want this to be the smallest possible. So if I am the market or the buyer, the kind of smart businessman who buys your production line, well, I want to pay the smallest possible price, which will still be fair enough. So this guarantees that you will accept. This guarantees that I will be satisfied if I did not overpay. I will minimize this. Okay, now a small miracle happens. This problem is exactly the dual to the original problem. If you look at this thing, I mean, here we have constraints corresponding to the columns of this matrix, here we have the constraints which correspond to the rows of this matrix. Here we have these numbers as the right-hand side of the constraints, here they appear in the objective function. Here we want to maximize something, here we want to minimize. That's exactly a pair of primal and dual problem. Let's try to see what our theorems tell us about whether we'll get a transaction here, whether this transaction will satisfy both sides, whether it's kind of efficient transaction. So let's talk about the big duality theorem. So let's say that this is a problem about the producer and this is a problem about, well, businessman. Who just buy the whole business. Maybe buyer. So big duality theorem tells you that the amount of profit that you will derive from the production, any feasible solution here, is is always more equal than the price which you get in this case. So profit for the producer is smaller or equal than the price the buyer, the businessman pays. So that's our big duality theory. It tells you if you formulated these constraints using our fairness conditions, using this kind of duality, using this logic, the price that will be offered to you will be always larger than the profit that you will derive from any schedule of production, including the optimal one. So if your business is suboptimal, well, your profit will be smaller. If it is optimal, well, you'll get the largest possible number on the left, but even this one will be smaller than the price that you will get from the market if you ask for these constraints. Strong duality theory tells you something about efficiency. It tells you that the largest profit that you can extract out of this factory, of this production line, is in fact exactly equal to the smallest price for which you will be able to sell. So it tells you largest profit kind of from the most efficient, let's not use efficient, most, not the most optimal production plan. Is in fact equal to the smallest fair price. By fair, I just mean satisfying these constraints for the business. So it tells you something about the efficiency of this kind of solution. You can make this transaction without changing you have your production line, you will sell it for the smallest price, you'll get exactly the same amount of dollars that you get by actually using this production line. And vice versa, if the businessman at some point gets bored, well, and doesn't want to actually produce the chairs and the tables, well, he can really convert it back using the same idea. I mean, he already paid some amount of money. This amount of money is exactly the amount of money he'll get from this business from producing the actual chairs and tables. So this conversion didn't have any kind of transaction costs. You can freely convert from the production line to the cost of resources, well, the smallest fair cost of resources. Okay, let's talk about what other theories do we have. We have so maybe the theorem about the last dictionary is not very interesting in economical terms, but the complementary slackness is very interesting. So for complementary slackness, I'll have to tell you what are the actual solutions. So I actually will tell you. So complementary slackness. So let me say the optimal solution for the primal happens to be x1 is 15, x2 equal to 0. So for now, I'll just tell you that this is the optimal solution. We'll check it in a second that it is optimal. So I tell you that the optimal plan is produce 15 chairs and don't produce any tables at all. So, check using check optimality using complementary settings. So, okay, I came to you and told you that this is the optimal solution. We now have the tool to check whether I was correct. We should check feasibility of this solution. So, for this we'll compute the slack variables. S1 is 50 minus 3 times 15, which is 5. It is definitely bigger than 0. So first constraint is satisfied. Second constraint is 50 minus 2 times 15, 20, also positive number. Last constraint, last constraint is 30 minus 2 times 15, 0, still non-negative. So the last constraint is actually pushed to its limit. The original numbers are bigger or equal than 0. The solution is feasible. So because this is bigger or equal than 0, solution is feasible. Let's write down the complementary surface conditions. So I know that if I have slack in this constraint, then the corresponding variable in the dual problem will be equal to 0. So here I have y1 equal to 0. I'll have y2 equal to 0, because once again here I have a slack, this is not 0. From here I can't tell anything. This constraint is pushed to its limit, and the number slackness tells me, well, in the pair S3, Y3, one of the numbers is 0, and this is already 0. But I also have the slack variables in the dual. So complementary slackness tells me in the pair x1, t1, where t1 is the slack variable for the dual, 1 should be equal to 0. One of the numbers should be 0. x1 is not 0, so the corresponding dual constraint must be pushed to its limit. No, should be no slack. So the dual constraint corresponding to x1 will is 3y1 plus 2y2 plus 2y3 is bigger or equal than 20. Now we know there is no slack, so there should be equality. 3y1 plus 2y2 plus 2y3 must be equal to 20. So basically, this constraint in the dual, the slack variable corresponding to this constraint must be equal to 0, so this inequality must be actual equality. Third step, let's solve these equations, which is very easy. y1 is equal to 0, y2 is equal to 0, y3 is, well, here I have 0 plus 0 plus 2 times y3 is 20, so y3 is 10. And check dual feasibility. Each one of those is positive, which is good. And the slack variables, well, the first one must be 0. We kind of solve in such a way that is 0. The second slack variable, which corresponds to 4 times y1 plus 2y plus y2 plus 2y3 minus 10. So if we get a positive number, then we are done. We have the optimal solution. If we get negative number, then the original was not optimal. So let's see what we get. 4y1 plus y2 plus 20 minus 10 is 10. Okay, it's positive. Now we check everything. We have feasible dual solution, feasible primal solution. They satisfy complementary slackness. We are done. Both are optimal. So this solution, x1 being 15, x2 being 0, is optimal. Now we actually are sure about this. Next, let's interpret this complementary slackness using our story about a businessman who wants to buy the business. So complementary slackness. So let's organize our variables and dual variables according to the complementary slackness. S1 is 5, S2 is 20, S3 is 0, and the corresponding pairs will be T1, T2, Y1, Y2, Y3. This will be 0, this will be 10, y1 will be 0, y2 will be 0, y3 will be 10. So we have this complementary sets. In each row, we have at least one of the numbers 0. Well, let's see what this thing tells us. What these things tell us. So why is it that T1 is actually 0? Why did they have to push these constraint to its limit? Let's think about it in terms of this buyer, of this producer and this business. The producer knows that in the optimal solution he will be producing chairs. So he actually will be producing chairs. The businessman knows that, well, he will get, for the price that he's paying, he will get 3 units of wood, 2 units of metal, and 2 units of labor. He will pay some price, and he knows that, he will pay some amount. He knows that the best thing that he can do with this is actually produce the chair and get out of it a profit of 20. And he knows that in the optimal plan for production, he will be producing chairs. But now remember that there are, according to the strong duality theorem, there are no transaction costs. He should be indifferent between paying for the wood, metal, and labor and actually producing the chair. And he does produce the chair. Conclusion, he should pay for the 3 units of wood, 2 units of metal, and 2 units of labor exactly 20. Because if he suggests paying 25, and later he wants to get profit from the actual wood, metal, and labor, he'll convert it to a chair, he'll only get 20. So he lost $5 on such a transaction. But we know that he's not going to lose money. There are no transaction costs. That's the strong duality theorem. So this complementary slackness tells us, well, you are producing 15 chairs, and on each chair you are not losing any money or you are not incurring any transaction costs. This price which you pay for the resources required for the chair must be exactly the same as the amount of profit that you will derive by actually producing the chair. So it is meaningful. Let's look at this there. Here we have a different kind of complementary slackness. Here, the businessman is actually overpaying for the resources for the tables. If he buys the resources required to construct a table, if he buys 4 units of wood, 1 unit of metal, 2 units of labor, he pays, well, 2 times by 3, so he pays $20. But by actually producing the table, he'll only get $10 back. So the question, is he stupid? Why did he agree to such a transaction? Why did he offer to pay $20 for the resources for the table, and he knows that he'll only get $10 from actually producing the table? The answer is no, he's not stupid. He knows in advance that he's not going to produce the tables. So this part is irrelevant for him. He doesn't care how much he will pay for the resources for the tables, because he's not going to produce the tables. So you know that if he overpays, he actually knew that he's not going to produce the tables. If this number is not 0, then this number must be 0. So that's the interpretation of this kind of slackness. The dual variable being slack, the original one must be equal to 0. And the dual constraint is slack, the corresponding original variable is 0. Okay, so we looked at the interpretation of this kind of slackness, this kind of slackness. Let's talk about this kind of slackness. The optimal price that is offered for buying the wood is 0. So you're selling the wood for a price of 0. Is it reasonable? I mean, a priori it sounds like it's a very strange decision to agree to sell the wood for 0. I mean, you're giving away something. But the thing is that this something is actually not that valuable for you. You have 50 units of wood. Even in the optimal production, how much wood are you using? Well, 3 times 15, 45 units, plus 4 times 0. So you are using 45 units of wood. You still have 5 units of wood left. It makes sense to sell it for any positive price. So any price, kind of $0.01, 1 cent, is good for you. Because now you sold something that you didn't need, you cannot convert it to a profit, you sold it for a profit of 1 cent per unit of wood. Well, unfortunately, you couldn't do this in a very efficient market because the businessman actually solved the dual problem. He knows that you will actually agree even to 0. You still have this extra capacity of wood. Well, he tells you, give it to me for free. And you're forced to agree because, well, you don't have anything to do with it. You can't convert it to chairs, you can't convert it to tables for profit. Well, you accept it. So this thing, extra capacity in wood, converts to 0 price for the wood. Similarly here, extra capacity for metal converts to 0 price for the metal. But something quite different happens for labor. You could use more labor. If you get 1 extra unit of labor, well, this constraint got pushed to its limit. If you, say, increase this 30 to 31, well, you know that the new optimal profit will increase by, well, 1 times the corresponding dual variable, by 10. So you could use more labor. And now you set the price for the labor at 10. You actually want the price that you get for each unit of labor to be equal to the increase in profit that this 1 unit of labor gives to your business. So if you actually are paying for labor, you use all the capacity in the labor. So this is about this complementary slackness. And finally, let me write down what I just said. If if the producer would buy extra resources, he would buy them, he would agree to buy them at prices for wood. Suppose you are the producer and you want to understand how much will I pay for 1 extra unit of wood. Well, the thing is, this unit of wood will not get converted to any extra profits. You know that the optimal production doesn't use all the wood. You still have a little bit of wood remaining right here. If you buy more wood, well, you have to throw out a little bit more, but you will not get more profit. So you are willing to pay for wood 0, which is exactly the dual variable. For metal, well, you are willing to pay for the same reason exactly 0. In the best kind of scenario, you are still left with 20 units of metal. If you can buy more, well, it's stupid for you to buy more. You will just throw out more. But labor, the story is quite different. You could use 1 more hour of labor. In fact, so 1 more unit of labor leads to an increase in profit of 1 times 3, which is 10. So the producer is willing to pay up to $10 per unit of labor. So that's about our last theorem that we mentioned today. The sensitivity of the optimal solution to the primal to small change in constraint is exactly the value of the dual variable. In this case, well, so this we are talking about this constraint. If we change the right hand side a little bit, let's say 1, how much will the objective function change? How much will the profit change? The answer is exactly by the value of the dual variable, which is 10. So in this sense, the dual variable is the price which you are willing to pay for 1 extra unit of capacity, 1 extra unit of the resources. So in this interpretation, the dual variables have kind of name in economics. They are called shadow prices of the resources. So they are the prices that you are willing to pay, the prices for which you are willing to buy extra capacity from the market. If you can buy at a lower price, well, you are happy, you can increase your profit. If you can only buy at a larger price, well, you will only decrease your profit by actually buying. Or vice versa, if you can sell at this price, then it's good. So they are the prices which are good for you. They are not the market prices. So there is nothing here about what the market actually suggests. Maybe your business is really bad business, and I mean, you're really, really inefficient, you produce chairs and derive very small profits for them, and nobody will ever pay you that much for your labor, well, could happen. But these prices are about what you as a producer, you as the owner of this kind of production are willing to pay for extra capacity for labor. The answer is 10. Extra capacity in metal or in wood, 0, because you cannot use this extra capacity to derive extra profits. So this is the calculation of the dual variables. Give them the name shadow prices. So now let me recall you the very first lecture. I told you a little story about Kantarovich, and I told you what was the official reason why he was not allowed to develop his theory of linear programming. And the reason was he gave name to these numbers, to these dual variables of objective prices. So he thought that they are actually prices which are dictated by your actual production, so they are objective. And the Marxist ideology told, well, you know what, there is no such thing as objective prices. Whatever you tell us, it's counter to our ideology. We do not accept such a theory, even if it's mathematically correct. So you should not develop any further. So
But that was
okay, so see you next time.
I got that.